Okay, 3, 2, 1, 0, we are ready. And so here we start with a new lecture of today. The new lecture of today is about flux, divergence, and Stokes theorem. It is the first lecture, and the main character of today is the flux. So the first part is, so let me put it a red color and magnify. So first is flux. So what is the flux? It is something that you already know. And you already know, you can imagine of having a pipe like this, so a cylindric pipe, and you want to know what is the flux of liquid through the section of this pipe, and so then the flux, of course, will depend on the speed of the liquid, because here the idea is the flux is the quantity of liquid. So intuitively the flux is nothing but flux is equal to the quantity of liquid crossing the section of the pipe. Okay, this is the idea, and of course it is proportional to the speed of the liquid. Okay, to be more precise, I should have said that this liquid crossing the section of the pipe in a given time, in the time unit, for instance. And of course, this is proportional to the speed of the liquid. Okay, but then you can generalize the idea of flux by, for instance, considering, for instance, a river. So here you have the river, this is the level of the river, and then there is a current, and you want, for some reason, for instance, you have something that is below the level of the river, and you want to understand which pressure is it going to undergo. And so, for instance, you are interested on the flux of the liquid around the surface, which is not orthogonal to the axis of the river. Okay, so it is not along the axis, but it has this strange direction here. So, what is the flux crossing? Of course, it depends on the speed, but not in all speed, because if the speed is the same, but it is parallel to the surface, then you have no flux around the surface. So, the same speed, but parallel to the surface, gives no flux through the surface. Okay, this is extremely important. This is very important to be understood, and so the message from this example is simply that the flux through a surface is proportional to the component of the velocity of the fluid, the component which is orthogonal to the surface. Okay, this is a very important notion. I repeat, here you see in this example, when you have a velocity which is parallel to the surface, then you don't have flux through the surface. It is like the liquid is going in this direction, just contouring the surface, but not passing through the surface. But when the velocity is really orthogonal to the surface, then the flux. So the quantity of liquid passing through the surface in the unit time is maximal. Of course, the surface can be imaginary, a sort of theoretical surface. So this may not be anything real or anything concrete. Just a geometric object. You want to know how much liquid passes through it. So this very short and very informal preliminary discussion has the purpose of familiarize, or better recall you, these two basic concepts. The two basic concepts or idea. The idea of flux through a surface and the idea of orthogonal component to a surface. Okay? They can be fixed in a much better way from the mathematical point of view. I don't do it, first of all, because I know many mathematical ideas have already been fixed by Professor Cudratillo in his lectures, so I don't want to talk about orientability, and also I will use normal vector by knowing that you already know them. But if you don't agree with that, write me, okay? However, I start assuming that you know what is a surface and what is a tangent plane to a surface, and what is the normal vector of the surface, what is the parameterization of a surface. Okay? I will not repeat it, if not extremely quickly or through some example. Here I want to pass to the flux, and the main idea now I want to introduce is that the concept of flux, the notion of flux, can be extended, extended from the velocity of a fluid. There is some problem here, of a fluid, to every vector field. This is the important fact, okay? And indeed, it is widely used for electromagnetic field. If you already studied a bit of electromagnetism, you learn that the idea of flux is extremely useful in that context. Okay. So, you go from the velocity of a fluid to every vector field, surfaces, whatever you want, and now we can recall you what is what is a surface and how the idea of being parallel or orthogonal to a surface generalize. Okay? So this is just an example of an exercise, if you want, that will recall us some basic notions. So, given a fluid with constant in the space, or better to say uniform density, suppose it equal to 1 in some suitable units, and suppose its velocity at the point x, y, z equals what? So here you take velocity of x, y, z, and velocity is a vector, then I will put vector, is equal to y along the vector I minus x along the vector j plus k. And here I want to adjust a bit the way of writing, because v is a vector, is a velocity vector. I, j, and k are the usual unit vectors along the x, y, and z axis. Okay? So the exercise ends up by saying that we have to compute the flux of the fluid through the portion of the paraboloid that you know very well from the course of geometry, paraboloid, and this is let me call it sigma, which is the set of x, y, z in R3, such that z is equal to x squared plus y squared and z less or equal 1. This is oriented so to say, be informal towards the top. Okay? What does it mean? So let us give a solution and then let us discuss also the various terms. So, first of all, a picture. A picture can always help in these cases, and as a picture here we start from the 3 axes, x, where there is the vector I, y, with the unit vector j, and z, z here, with the unit vector k. So the paraboloid here is x squared plus y squared z less or equal to 1. So, first of all, This Cartesian definition of the surface is basically useless. Because it does not give us the orientation. So parametric definition, the parametric description, is much better. Let me try to understand why. First of all, what is towards the top? It means that at every point, the normal vector, so the vector which is orthogonal to the surface, must be oriented in the high direction. So if you are here, the orthogonal direction is this one. Then you are allowed to choose two different directions for the vector. One direction is here and the other one is here. But with this choice, you have that your normal vector points towards points downwards, and this points upwards. So since we decided, whatever it means, to orientate our surface towards the top, then we have to choose the upward direction. But how to do it mathematically, writing down some formulas and so on? We have to use the parametric description. So you already know how to do. In order to describe a surface, you need two parameters. Typically, they are defined as being u and v. And so you define parameter u to be equal to x, the parameter v to be equal to y, and then you have that z will be u squared plus v squared. This is a very simple and particular case because the surface is given as a graph, the graph of the function of two variables x and y, which is x squared plus y squared. So when you have a graph, you can always parameterize like that. But write it in a more usual way. When you have a parameterization, you have that the position of the points you are interested in are the following. You have u along I and v along j, and this is the meaning of these two positions, u equal to x, v equal to y, and then you have plus u squared plus v squared k. And now you have to bound the range of your parameters u and v. How to bound them? Notice that here it is stated that z must be less or equal to 1. So for instance, z equal to 1 ends up here. And this means that the domain of our parameterization must be the set of all couples of uv in R2 such that u squared plus u, oh sorry, there is a problem here. Oop. I lost my pen. I have to recharge it just 30 seconds. So I will use this 30 seconds just to tell you that this point is extremely important, the passage from Cartesian to parametric description of surface. And this is very important just because by the parametric expression you can have formulas, analytic expression for the normal vector, which is very important here when dealing with surfaces, which gives you the orientation of surfaces. So uv in R2 such that u squared plus v squared is less or equal than 1. Okay? Now, why parametric? So I want to write this fact by parametric description of a surface. One can easily write down the normal vector at every point, and therefore choose the orientation. Let us see how to do that. We have to differentiate R with respect to u first. So you have I plus 2uk, and then R with respect to v, and then you have j plus 2vk. So what are we doing? We are doing this. Consider this point P here, and so there are u and v, and R, when you are moving u and v remains the same, it means that you are moving x, so you are doing this. This is obtained at uv fixed. On the other hand, when you are moving v, then if u fixed, then you are moving like that. Do you see that when moving both, then you recover all the surface? But now, what happens when you differentiate? When you differentiate with respect to u, so v is fixed, then you find a vector that it is in this direction, which is tangent to the purple curve, because v remains fixed. So you move u, so you are tracing this curve on the surface, and then when you differentiate it, you have a tangent to this curve, and so you are here. Vice versa, when u is fixed and you are moving v, what you do is to draw this curve here, and then what you are doing is to find another tangent like that. These two vectors that you find differentiated are both tangent to the surface at the point you chose, so they generate, since they are not parallel, they generate the tangent plane to the surface. What does it mean? It means that they are both orthogonal to the normal vector at the surface at the point you chose. So in order to find the normal vector, the only thing that you have to do is to compute the cross product between dr du and dr dv. This you can do by writing down the determinant as usual, but also in another way you can do this. You can write down I plus 2uk cross j plus 2vk, and this is I cross j plus 2uk cross j plus 2vi. Sorry, this is a wedge and it is equivalent, but we use cross by 4uvk cross k. So what happens? I cross j is equal to k. Remember the order ijk. So ijk does not contain the string kj, ijk. So you have to reverse the order in order to find kj, and so this means that this product is not I but minus I. This is just a quick method to do that. Again, ijk, you don't have ik, you have ki, so it is reversed, so it is minus j. And k cross k is equal to 0, because the cross product of two parallel vectors is 0. So you have k minus 2ui minus 2vj. Now, by this method, you end up with one normal vector, not the normal vector. The normal vector does not exist. It is unique up to a non-zero factor. But what we need is an orientation upwards. And upwards means that the z component must be positive. And here is the z component. So the z component is equal to 1, larger than 0. So the orientation here is upwards. And this is exactly what we were looking for.